Okay, so one of the big things this week, we're focusing on functions, what they are, function notation. Our discussion this week is about functions. Like, this is a really big concept, especially when you're going to be going into calculus. If you have to go on to take calculus, functions is a really important part of that. So, definition of a function. So this is the mathy definition of a function. A function f from a set A to a set B. And a set is just like a group of numbers or just a collection of things. So it's a relation, and a relation just means that there's some sort of relationship between these things. So a function from a set A to a set B is a relation that assigns to each element x in the set A exactly one element in the set B. So this is basically an input-output relationship where you're plugging in a number x and you're getting out a number y. And every input only has one output. So you can't have a number for x and have two different y values. If it does, it's not a function. A function specifically is one in, one out. Now you could have multiple inputs going in the same output number. That's okay, just as long as each input only has one output. That input we call the independent variable, and the output is the dependent variable. And when we're graphing, we always have the input along the horizontal, output as the vertical. So the independent variable is the thing that you are not necessarily changing. And then the dependent is what is changing based off of the independent variable. So when you're looking at word problems, which we frequently have, all of our application assignments are literally applications of the math. Anything with time is always an input. It's always an independent variable because that's not something we can't control time. And we're usually looking at, as time goes on, what changes based off of that time. So we're looking at like cost per time, or maybe your speed over time. Cost and speed would be those dependent variables because those are the things that are your output, or basically what is depending on time. So functions are very intertwined with the science principles of independent and dependent variables. So general characteristics of a function. Each element in A must be matched with an element in B. So what this means is if you're plugging in a value for x, you must have some sort of output. You can't plug in a value and then not have no output at all. So anything that is in the set has to go to something. Some elements in B may not be matched with any element in A. So this means you could have some outputs that don't have an x that goes to it, no input. That's okay. That's completely fine. You don't have to hit every y value, but you want to make sure that all of your x go somewhere. Two or more elements in A may be matched with the same element in B. And I mentioned this, you could have two different x values having the same output value. That's okay. And then an element in A and the domain, this we will talk about what domain is later, but we call this the domain, cannot be matched with two different elements in B. So your input can't have two different y values with it. So these are just kind of variations. It's just a little intricacies about a function, some things that could happen that can't happen. So there are different ways to represent a function. You're going to see this on or in the application assignment, all the different ways to represent functions. So we've got verbally. And so that is a sentence that describes how the input variable is related to the output variable. So a lot of word problems are described verbally, and we have one of those on our application assignments where you're given a function and it's described in words, and you have to create the equation based off of that. Numerically means that you've got numbers that are giving your function. So that's usually given as a table or a list of ordered pairs, and you're specifically matching your input to the output. So we do have a problem on the application assignment that is a table that you're filling in, and that's you're given a function there. Then we've got graphically. So you can have points on your coordinate plane on your graph. Your horizontal positions, I mentioned this, are the input, your vertical is the output. And we do have a function, number 5 on the application assignment, that is represented graphically. And then algebraically is where you're actually given an equation. And so that we have 2 variables. We'll have our input and then our output, and then that gives us a function. So we're going to go through some examples here. We're going to go through with all of the different ways you can see a function represented and determine, are these actually functions? Because you can represent something with numbers here like we have numerically, and it may not necessarily be a function, but it is one way that we do represent functions. So the first example here, we've got our domain, which we call the X, and then the range, which we call Y. And later I'll go into more detail on domain and range, but just know that those are our X and our Y. And so the key that we're looking for here is the relationship. Does every input value only go to one output value? So when you see it represented like this, you're looking for basically, does an input have only one arrow from it? Because that means it's only mapping to one Y value. So if you ever have an input here that has 2 arrows going from it, that means it's not a function. So for our first example here, we've got a problem with the number -1 here, because -1 has 2 arrows that are going from it. So that actually violates our definition of a function, because we've got an arrow going to 0 and then an arrow going to 1. So that value has 2 outputs, and that violates our definition of a function, because our input can only have 1 output. So it's okay that the number 2 has 2 inputs going to it. We just can't have an input have 2 outputs. So that means that this is not a function. So second example, you're looking at the same thing. You're just making sure that every input value only has 1 arrow going from it. And it has to have an arrow. It can't have 0 arrows, because everything in your domain has to map to something. So each of our numbers on the left, -2, -1, 0, 1, and 2, only have 1 arrow going from it to a Y value, and that makes it a function. So it's pretty straightforward when you're looking at just a series of numbers and you've got these kind of arrows mapping, because you're just looking at, are there 2 outputs, 2 arrows coming from something? Then it's not a function. Otherwise, it's a function. So pretty straightforward. Are there any questions on this example? All right. So next we've got these in table form. And so we've got two different tables here. On the left, we've got 10 going to 3, 7 going to 6, 4 to 9, 7 to 12, and then 10 to 15. So I want you guys to take a look at this first table and then tell me, is this a function or not a function, and then why or why not? So you can type it in the chat, or if somebody wants to unmute themselves and wants to do it verbally, that's totally okay. It's up to you and your comfort level. Okay, so Jared says yes, because every input maps to its own output. So we see every number here on the left has an output on the right. Do we have other? Okay, we've got a no, because it repeats 10. So we have 10 going to 3 and 10 going to 15.
There's also 7 repeating itself there too.
That is correct. 7 is going to 6 and 7 is going to 12. So while yes, every input has an output to it, we do have repeats. And this is where seeing a function in a table can be a little confusing because you have to look to see if you have repeated x. Because usually when we have a table, we don't list two y's there. We will list only one y value, and then we might list the x twice. So tables are a little tricky like that. And so sometimes what I do is I will just kind of make my own little mapping. So I've got 10 going to 3, 7 to 6, 4 to 9, and then I've got 12. So then I've got 7 going to 12, and then we have 15, and 10 is going to 15. So sometimes you have to kind of make your own little arrow chart to kind of see, oh, even though every x has a y associated with it, there's actually, it's repeating some x values. And if it repeats, we have to be careful. And you can't just say, oh, it's repeated x. You have to make sure that if you're repeating x, you're also got different y's. Because I could have like 10 on there twice, but if both of the y's are 15, then it's not really repeated. It's the same thing. So you have to be a little bit careful there. So this is not function. How about the second one? So we've got -2, 0, 2, 4, and 6, and then 1, 1, 1, 1, 1. So is that a function y or why not?
I would say it has a potential for a function because they all only have one output. Even though they're all the same output, it's still only one output.
So there's only one output. They're all the same output. Any other thoughts? Anybody agree, disagree? Yes, because they're not more than one of the same output. Okay, so we've got agree. So this is indeed a function. And the one thing you want to be careful, in addition to the fact that, okay, they've got this repeated output, you want to make sure that you don't see x repeated more than once. So as long as if you're looking on the left and you don't have a repeated x when it's in table form, it's automatically going to be a function. So we don't really care what the output is. We just have to make sure we're not repeating an x value. If you've got a repeated x value, then you have to kind of look at what those outputs are to see, is it the same exact output as the other x that I saw, or is it a different one? So because we don't have any repeated x values here, that automatically makes it a function. So we don't care that the y is 1. That's totally okay. Okay, so now these are sets. So these are sets, which means that it specifically has the curly braces, and we've got sets of ordered pairs. So this is still numerically, though I do throw in some letters there in the other two. So technically, we're not using numbers, but you can have, you can be mapping things that aren't always numerical. You can have things that are not numerical things we saw in the discussion. As long as there's this input-output relationship, they don't necessarily have to be numbers in and numbers out. So what you're looking for here is, again, you're looking for first, when I'm looking at my ordered pairs, are there any repeated x values? And then if there are no repeated x values, it's automatically a function. But if you do have repeated x values, you need to check, do those x values have different y values, or are they repeating the same y value? So that's what you're looking for here. So for the first one, we've got an ordered pair of 0, 1, then we've got 1, -2, then 2, 0, and then 3, 2. So you're looking at all of the x values, and in an ordered pair, that's always the first value. So first you're looking for, am I repeating any x value? So our x's are 0, 1, 2, and 3. There's no repeats there. So that automatically means this is a function. You don't care what the y values are. You're just making sure that you don't have any repetition here. So next one, we've got 0, -1, 2, 2, 1, -2, 3, 0, and then 1, 1. So I'm going to highlight my X values here. Makes it a little bit easier. And then we're saying, okay, are we repeating X values? So we've got 0, 2, 1, 3, and then we've got 1 again. So we've got these two order pairs where we have an X value of 1. So we have to look more closely at it and say, do these have the same Y value? And they don't. There's two different Y values, which means that our input 1 is going to two different Y, and that violates the definition of a function. So that makes this not a function. So let's look at the next one. We've got C0, B0, and A3. So what do you guys think? Do you think this is a function or not a function, and why or why not?
Function, there's no repeated X's.
Yes, so this is a function. We don't have anything input that's repeated. Our inputs are C, B, and A, nothing is repeated. What about the next one?
Not a function, C is repeated.
That is correct. So we do have C twice here. And you have to make sure if it's repeated that it's also, you either got the same or different Y values, and the Y values are different. So that means it's not a function. And you can always make a chart with these as well. Like I can say A is going to 1, C is going to 2, C is also going to 3, and then B is going to 3. So you can do a little arrow chart and see that your input C has two different Y values or two different outputs. And so that makes it not a function. Are there any questions?
So you lightly touched on the fact that sometimes the same numbers could be repeated, where it has, like, say if that was C2, C2, then that would have made it a function versus it being C3.
Yes, and usually you won't see it necessarily written that way. You may see something where you've got a set and say we've got A1 and maybe you've got C2, but maybe like however these are calculated, you may also see it written something differently. Whoops, I didn't mean to change that. Let me write this a little better, where maybe instead of 2, you might see it written as 4/2, which looks like you've got two different outputs, but 4/2 is equal to 2, so that would be a function. So you won't necessarily see it, the actual numbers like listed twice. It might be listed in another form, but it's equivalent when you simplify it. Okay. So now we have equations, and equations are harder to see whether it's a function or not. The way that I usually determine if a function or if an equation is a function is I usually end up graphing it. So when you have a graph and you're determining if something is a function, you have what is called the vertical line test, where if I draw a vertical line through any portion of that graph, I only hit my graphed part once. If you hit the graph part more than once, then it's not a function. It violates the horizontal line test. So I like to do these by just throwing it into a graphing calculator and then graphing it. But there are other ways to do it as well. And one of the things that when you're at this level of math and you're going to be going on to calculus and you have to go into, higher levels of math, you also want to learn what the equations look like just from the equation and learn what the graph looks like so that you know immediately, you don't even need to graph it. You just know this is this type of equation. This is what the graph looks like. So I know immediately if it's a function or not. So there are certain things called parent functions, which are talked about in college algebra. And those are, a function of a specific form. It's going to be a function if it has this particular shape, or if the equation looks like this, or you can make it look like this. So something like this, you can throw it in a graphing calculator, or you can say, I know that it's this type of equation, so I know what it's going to look like, and I know whether it's a function or not. Then the third way is to solve for y, and then see if when you're solving, you would end up with two possible y's, like maybe two different y equations for y. And if you do, then that means it's not a function, because now you just got two different y values. So that is what our textbook does, is it says solve for y, and then from there determine whether it's a function or not. So we're going to go with that method for these two. And then I'm also going to say, okay, well, this is how I know, based without doing that, whether these are functions or not. So we'll take the first one. We've got x squared minus y equals 9. So if we want to solve for y, we can subtract x squared from both sides. And so that gives you a minus y, and then we get a 9 minus x squared. So it doesn't matter if you put your x squared before the y, or before the 9 or after the 9. It really doesn't matter, just as long as you have it there and you have the correct signs. So because we have that x squared minus y, it's still a minus y there. And then I subtracted x squared. Then we want a positive y when we're solving. So you're going to divide everything by -1, which basically just flips the signs. And so you get y equals -9 plus x squared. So now we've solved for y. We have only one equation for y. So that means that this is going to be a function, because we didn't get a second equation when we were solving. Let's look at the second one. We've got x squared plus y squared equals 9. So the only difference here is that we've got a y squared, and then it's a plus instead of a minus. Very minor difference. So again, I'm going to subtract x squared from both sides. So this gives me y squared equals 9 minus x squared. Now to solve for y, we need to take the square root. And when you're solving and you take a square root, you always get a plus and minus. So we're going to get y equals plus or minus 9 minus, or the square root of 9 minus x squared. And now we have two equations for y. We have y equals the square root of 9 minus x squared, and we have y equals the negative square root of 9 minus x squared. So we got two functions for y, which means that there would be two output values, which makes this not a function. So first one's a function, second one is not, just very minor details in basically the sign of the y and the exponent on the y. So the one on the left, I know that this is a function just by looking at the equation, because if you don't have an exponent on the y, it's going to give you one value when you solve for y. So if there's no exponent on the y, it's automatically going to be a function. I also know that this is a function because I know that this equation, when you solve for y, gives you a quadratic equation, or it gives you a parabola. And I know that the shape of a parabola is a U, and that passes my vertical line test. So I know that this is a parent function of something that's x squared. And so I know what it's going to look like. And then I know just by visualizing it in my head that this is a function. The one on the right, I know that this is not a function because that equation in that form is the equation for a circle. So an x squared and a y squared give you a circle. Though we will learn in week 7 that there are other types of equations you can get from an x squared and y squared, depending on the sign in front of the y and some other things. So you can also get other types of equations, but generally x squared plus y squared equals something is a circle. And circles are not functions because when you do the vertical line test, you're going to hit the graph twice. So if you really learn what an equation looks like and learn what the shape of it looks like when you graph it, you don't even need to go through the algebra here to determine if it's a function or not a function. Now, the website that I recommend for doing all types of graphing is Desmos. So I'm going to just pull this up. So it's desmos.com. So this is a fantastic website that I recommend you bookmark. You can see that it defaults graphing calculator, but if you hit math tools, there's also a scientific calculator, which will be very handy. And then there's a matrix calculator, which will be very handy because in week 3, we do matrices. So great. You don't need to sign up for a class or anything. You just hit graphing calculator. And then you get this window. And then this is where you type in your equation. And it doesn't have to be solved for y or anything. You just type in what you see. So I've got my x. And then to get into the exponent, the keyboard shortcut is the little caret symbol above the 6. So you just hit shift and then you hit the 6 and you get up into your exponent. And then I can type that 2. And then I have to hit the arrow key to get out of there. And then minus y equals 9. So that was our first equation that we got. And you can see this is a shape of a parabola. It's a U. No matter where I have a vertical line, I'm only going to hit my graph thing once. You know, the red is our graph. So if you don't use the keyboard and you want to get to the exponents, there's a little on-screen keyboard here, and then it does have buttons for exponents that you can use, like things for square roots. If you have to graph something to square root, we've got absolute value. So there's a lot of stuff here. If you want another graph, you just hit underneath it and then it makes you another line. To turn this one off, you just hit here. So then you don't see it, but you don't kind of lose your equation. So the second equation we had was x squared plus y squared equals 9. So you can see, you type that in, you get a circle. And so this violates your vertical line test, because if I draw a vertical line, I am going to hit this graph in more than one place. So that makes it not a function. So the quickest way to determine whether an equation is a function or not is just to literally graph it. And so this website, fantastic way to do it. Are there any questions?
Hi, Stephanie. I have a question.
Sure, go ahead.
I get how to figure out if it's a function or not, and I'm going to get really elementary. And why do we care if it's a function or not?
Why do we care? Because there are certain things that we can do to functions, but not do to other things. So a lot of graphing, we specifically want to have functions. And let me take a real world example here where you want something to be a function. And let's say you got the letter grades of a student and you want to determine who was the best student, you know, who actually had the highest score or whatever. If all you have are letter grades, so your letter grades would be your input, and then the output would be like the actual percentage that you want to compare. A letter grade of A has lots of possible outputs to it. You know, you could get a 90 and get an A. You could get a 99 and get an A. You could get 100 and get an A. You could, maybe with extra credit, get above 100 and get an A. So if you are trying to rank maybe students in a class and all you have are the letter grades, it's not a function because the input has multiple outputs with it. And you can't actually really do what you want to do. But let's say you were given instead the percentages and then, you had your percentages, and then you had the letter grade A, you have with your input being percentages, you can do it what it is that you want to do. So you can actually rank the students that say that you want to. And so you want to be given data that is a function, because it allows you to do more analysis on it and actually be able to come up with actual answers, because if it's not a function, you have a lot of unknowns. I actually, several years ago, our data team was trying to run some data to determine, what kind of students are not signing up for their next classes. And the information they had was not a function. So they couldn't actually get an answer. Like, they wanted to know, like, is there a specific letter grade or something that says this student's not going to sign up, or this student's going to sign up, or things like that. But they didn't actually have the data that they had was collected in such a way that there were too many possibilities of outputs. Like, I couldn't analyze that data and say, okay, these are the types of students that, are going to do this or this. And it just, you don't have the right data, because they were taking some existing data and trying to work backwards to what the original was that collected that data. And they couldn't do it because it wasn't a function. There was too many possibilities that could get to where they were trying to go. So whenever you're trying to do stuff with numbers, you really, really do want things to be functions, because it just makes your life easier. So that's why we care. As you can do stuff without functions, it's just sometimes you can't get the granularity that you want if things are not functions. And for people that are in computer science, you definitely, anything you want to code, you want to make sure it's a function, because otherwise your program, if there's more than one possible output of your program, is going to have issues because a computer needs to have one input to every output. And so you have to be able to say, okay, it does this, it knows where to go next. And if it doesn't know where to go after that, because there's more than one output, you're in trouble. So yes, so functions are really helpful when you're looking at data, because it really allows you to narrow down the data and get more granular and actually come up with useful results from that. Functions are useful in computer science so that the computer actually knows where to go. It's just, even if for those that are going into engineering technology, you're going to be doing everything that you have is going to be working with functions, because you don't want to build a circuit and then be like, well, if you plug in, say, this voltage to the circuit, I don't know what the output current is going to be. It might be this current, it might be this current. I don't know, you can't plan for that. You don't want to plan for that. So you want to make sure that whatever you go in, there's going to be an output associated with it. So functions are the key to any kind of useful math that we have. Now, when we get to calculus, we do stuff with things that are not functions. There are places where a circle is actually very helpful, and with trig, circles are very helpful. So we're not always working with functions, but it is very, very common that what you do are functions. Okay, so function notation. So this is where I see a lot of people get messed up, because they understand the concept of a function, but they get confused with the actual notation. And notation is so important in math. You have to know what every little symbol means. You have to know when symbols are grouped together, when they're separate, because there are places when we're talking about domain and range where a parenthesis is different from a bracket. So they don't mean the same thing. You have to know the difference between those, or a difference between a closed circle and an open circle on a graph. All of that is really, really important. So function notation we use specifically when we have functions. And it basically means instead of using y, we use f of x. So that's how we read the f parenthesis x parenthesis f of x. So f is your name of the function, and default is f just to stand for function. X is your input value, And then we call the whole thing f of x the output, and that is like the value when you're plugging into that particular input x. So when you're told to look for function values, you're looking for output values. So function notation is very useful. For one, if you have an equation in function notation, you automatically know it's a function. So fantastic. Two, it allows you to give different equations different names instead of just reusing y. So it helps kind of keep things organized. If you have a function f and a function g, and you're doing a lot of work with these equations, by calling them f and g instead of just y and y, it helps you keep them apart. And you can, instead of just naming them like f and g, you can actually name them useful things. Like we'll use c for cost. In business, you'll see c of x for cost of x, and you'll see r for revenue, P for profit. So there'll actually be letters that stand for something that helps you actually understand what the equation is actually telling you. Because if your equation just has y, you don't know if that equation represents something in real life. That may be meaningless for you. But if you see something that's like h of t, h usually means height. So that says, oh, this equation is telling me that it's giving me the height of something. And then it tells you what that input is. And that also is useful. T is always used for time. So we don't always use X, we might use T. So that's useful information. So H of T is saying, this is giving me the height of something over time. So by using function notation, it's giving you more information about the equation that you're actually working with. And it's really nice because if you see something like H of 2, it's telling you what number you plugged in to get that particular output value. So if somebody just said y is equal to 10, you don't know what the number was that was plugged into that equation in order to get that value. But if somebody said f of 5 is equal to 10, you know, oh, when I plug in 5, then this is my output 10. So it just gives you a lot more information. So that's why we use function notation, because we like to work with functions because they're easier and the notation gives us more information. So the key thing about this function notation is that it's not multiplication of some variable x by some variable or f. That's not multiplication there. The f of x stuff, function notation, is a group of things that are not separated. We're not solving for f or anything. It's kind of grouped together. So you do have to know when you see things in this notation, you're not trying to solve for f. You're not solving for x. It's a grouped together as one thing. If there was no parentheses, like if it was fx without the parentheses, that would indicate that these are seen as multiplication. But if they're written together with the parentheses, it's function notation. So the other nice thing about functions, and you'll see this in the example on the right here, is that you can plug things into a function with different variables, so you can like change the variable, kind of like a unit conversion. Like if you have an equation for height and the output is in feet, you can plug in a different input value that will convert it to miles or something like that. So that's the other nice thing about using function notation, is that you can actually plug something in and then get a new equation that is now in a different unit. So that's actually what you'll see with the example on the right here. But on the left, I just have f of x equals 3x minus 5. And then we want to find f of negative 2. So f of negative 2 is telling us that our input x is negative 2. So when you're finding function values, if you first determine, okay, what am I inputting, which is negative 2 here. So then you also replace x with negative 2 on the right. So instead of 3x minus 5, it's 3 times negative 2 minus 5. And then finding function values means evaluating, and evaluating is not solving. So you are not solving for f. All you are doing now is doing the order of operations on the right side, because we're looking for f of negative 2 on the left. So now we just have to do the order of operations on the right. So 3 times -2 is -6. So we have -6 minus 5, and that gives us -11. So I then like to write my final answer in our function notation here. We're finding f of -2. So f of -2 is equal to -11. So it told us when you plug in this value into this function, our output is -11. We're not solving for f. We're just finding what is f of -2. And so then you're only working on the right. Now the example on the right, this is a good example of how you can kind of change units here in a way. So we have v of r equals 4/3 pi r cubed. This is actually the formula for volume of a sphere. Then we want to find v of 2r. 2r is essentially the diameter, because 2 times the radius of a circle is a diameter. So this formula is basically finding v of 2r is like you're converting your formula that is in radius, and you're now converting it to a formula in terms of diameter, because you're kind of replacing your r to 2r kind of thing. It's like you're doing a conversion here. Now, what the output here is not actually going to be the formula if we're trying to convert it to diameter, because we'd have to, it'd be a little bit different. This is, you would be, if we wanted to actually convert it to like where you're plugging in the diameter, we would actually end up being divided by 2. We would have, I think, r divided by 2 to convert it to diameter. But the thought is here, like you're converting it to another unit. Like you've got r, and now you've got twice r. That's like a diameter here. You can think of this as actually, because we're not specifically plugging in the variable d for diameter, that we're kind of finding it the volume of a sphere that's like twice as big for the radius. If you wanted to always make a sphere that's twice as bigger than the radius, like, you know, you're creating a new function here. And so our output formula is like going to be a different formula for a specific type of sphere where your radius is twice the radius, essentially. That probably sounded very confusing. But to do this, we have this formula for v of r, and now we want 2r. So what this means is everywhere we see r in the original function, we're replacing it with 2r. So instead of r cubed, it's now 2r cubed. And then we need to follow the order of operations on the right, which means we're basically simplifying the right side. We're still going to have an r in our formula. So 2r cubed, you need to cube the 2 and cube the r. So we have 4/3 pi. 2 cubed is 8, and then we have r cubed. And then we have the 4/3 times the 8, which is 32/3 pi r cubed. So we now have a new formula. V of 2r equals 32/3 pi r cubed. So this would be, you know, let's say you have your radius of your sphere, and now you want to find, and that gave you the volume, and now you're like, well, what happens if what is the volume for a sphere that's twice the radius? You now have a new formula that would determine the volume for a sphere where the radius is always twice the other sphere. So what's nice about function notation in this case is by on the left saying it's 2r versus r is that you know that you're looking for, you're getting the output for something that's twice the radius. So it's telling you specifically what you're plugging in and then what your volume is that you're outputting, so that you're not losing that information, that you don't have this new equation for volume and you think, oh, it's just the size of I'm just plugging in any old radius. You know that this is specifically for something that has twice the long radius of whatever you're interested in. So it does give you a little bit more information by having it in the function notation versus your original notation. Okay. Just as a side note, because I didn't actually put this in my presentation, but one example of, like, you can even put functions inside of another functions, and that's actually something that you do in calculus, is you take one equation, you're plugging it into another equation, and it's called a function composition, and that is actually one of the things that you guys do learn this week. But one helpful example of a function composition in real life would be if you have an equation for determining the cost of some product if you own a business, but then you know that you have tax on top of that. So you might have an equation that helps you figure out tax, and then an equation that helps you figure out the cost of your product or whatever you're selling it for. And then if you take that cost for the product equation and you plug it into the tax equation, it will give you the cost after tax, basically, because then it's applying tax on top of your existing equation. So that's one way where you might actually plug an equation into another equation, or a function inside another function. Is like you have something and then you're like, oh, now I'm doing tax on top of that. So I'm not doing function compositions specifically in here, but that is another use of the function notation. So like I said, I mentioned domain and range very briefly at the very beginning. So the set of inputs to a function is what we call the domain. And then the set of outputs of the function is called the range. So this is used very common, domain and range. You'll hear that a lot with functions. When we're writing domain and range, so there's two different ways that we usually write our answers. If you have a function and you're given it as in a form of a table, or it's like a set of ordered pairs, or a non-continuous graph. And I shouldn't necessarily say non-continuous graph, because you can have non-continuous graphs that you do write in a different notation. What I really should say is a graph of points, where you don't have anything that's connected, as you just have points that are plotted. Basically, you're only graphing ordered pairs. So if you only have distinct ordered pairs via through table or set or on the graph, you give your domain and range in set notation, where your domain is going to be your listed X values in curly braces, because that's representing a set. And then your range would also be listed as a distinct list of values in curly braces, because you don't have things that are connected. With a table, all you have are these ordered pairs. You don't have all the values connected between them. So you're literally just listing every X value and then listing every Y value. If you have a function and it's given as an equation, or you've got a graph that's continuous, which means there's no gaps, or I should say, or the graph has continuous parts. And what that means is you might have a spot that has a gap between another spot, but there are parts where it's like there are no gaps, where it's just a line or a curve or things like that, where you don't lift off your pencil. Because if you see a curve on a graph, or if it's any spot where you don't lift off a pencil, you basically have every single possible number between the two endpoints, and you cannot list all of those, because there's an infinite number of points between here and here if I'm connecting them with a line. This is like how you don't want to list every single possible value in between there, because you get into these absolutely tiny fractions. That's basically impossible. So for those types of things, equations, and then we've got graphs, or you've got things that are continuous, then you have to give your domain and range an interval notation. An interval notation is where you're using parentheses and brackets. Parentheses are indicating that the endpoints are not included. If you have like an open circle on a graph, and brackets indicate that it is included. So that'd be like if you have a closed circle on a graph or it distinctly stops somewhere. So when we write domain and range, we have two different ways to write it. And generally, when you see a graph, it's going to be an interval notation. Otherwise, if it's like a table or set of ordered points, it's going to be set notation where you list each X and Y value. And then the last thing that I wanted to touch on here is piecewise defined functions. And so these are functions that may have a gap, but they're still functions because they still have an input going to an output. And it looks like there might be two different outputs, or an input has two different outputs, but they don't, because we're restricting it for specific values. So you've got two different equations, so two different outputs, but they're not true for every X. For one set of X, one equation is true. And then for the second set of X, a different equation is true, so that they don't actually, every X only has one output, because we're saying it's only true within this portion of the domain, so that there isn't any overlap there. So that's what makes it piecewise defined, is you're just saying we've got these different pieces, and then each one has a different X value that goes with it. So this is just my last example here. I know that this is already, we're basically at the hour mark. So maybe I will just do the middle example here. I'll just do f of -1, or I could probably do all three. It wouldn't take that long. But we want to find the following function values for this function defined. We've got f of x equals, and then we've got -3x minus 3 when x is less than -1. And then we have x squared plus 2x minus 1 when x is greater than or equal to -1. So when you're finding function values of a piecewise function, you have to determine that x value that they're giving me, which equation am I matching with? So we've got our input of -2 here for f of -2. So x is -2. So for an x value of -2, that's going to be -2 is less than -1. So we're going to use the first equation, the -3x minus 3, because that equation is true when x is less than -1. And so -2 is less than -1, so we're using that equation. So I need to replace my x here with -2. Let's just rewrite this whole thing. And then we find that function value. So we're going to get 6 minus 3, and then we get 3. Next one here, I have f of -1. So which equation is true when x is -1? So in this case, if you're finding f of -1, we need to use, there we go. We need to use the second equation, because that is true when x is greater than or equal to -1. So when f is equal to -1, the second equation is true. So we need to plug in -1 into the second equation. So when we evaluate this, -1 squared is 1. 2 times -1 is -2. Then we've got -1. And you get -2 out. Then if we say f of 1, what's f of 1? Well, 1 is greater than -1, so we use the second equation as well. And my stylus seems to be dying, so this is a good thing this is my last one. So we just plug in 1 into that second equation, and that gives us 1 plus 2 minus 1, and it gives us an output of 2. So for piecewise functions, you have to pay attention to that domain, which is the inequalities there, so that you know which part of the equation you're using when. And that ensures us that we don't have any overlapping outputs, and it makes it a function because you've got it like sectioned off for each part. All right. Well, this is just a very small part of functions that you guys have in the reading this week. There's so much more to functions. There's like finding zeros of functions. Number 5 on the application assignment, you're looking for the zeros, you're looking for, you've got, questions about intercepts, what's the domain, what's the range. Like, I didn't go into any of that kind of stuff. This is like an introduction to the basics. But I do have a video specifically that let me actually open up our class and I'll pull it over here. So like I said, right underneath the discussions, there's a link to videos. So week 1, they've got tons of extra videos here. So if you need videos on like the midpoint formula, all of these kind of things, slope, there is a problem on linear depreciation. So if you're stuck on that homework problem, you might want to watch this one. These videos are going into more detail. Basically, I have kind of gone through 4 of these. I didn't do domain. It's like I'm kind of redoing these videos right now. So that's what I'm doing here. And then this last one is going to be helpful for the very last problem on the assignment, the application assignment. So because that has questions on zeros, increasing, decreasing constant, the relative minima and maxima. So those are answered in this video. So you'd want to watch this last one if you're stuck on that last problem. Other than that, there are tons of videos in our weekly content as well that do a fantastic job. Like there's so many resources here. You've got more resources than you need. But like we've got tons of these videos. Half of these are coming from the textbook itself, has tons of videos. And then the other half are just videos found on YouTube. So, the thing about learning is my method may not work for you. You may not like my explanations. There may be somebody else that you like better. So that's why we have so many options for you. So you can choose to watch these videos. You can choose mine. You can do both, whatever you need. You don't have to go through all of these, pick what works for you and your learning style. And then, so there's tutorials, you've got all this stuff here, but all right, so that's all I have for you guys for today. Any questions about the course or anything like that I can answer? Okay, Chris, so that was a virus on the links connected to Larson pre-calculus. That's not good. That's the publisher's textbooks. I'm just opening. Was it a pop-up that happened? Because I've been on this website tons of times and I've never had any issues with it.
It was when I first clicked the link, it was doing it wasn't a pop-up thing. It was making me click allow or block before it would let me go into the video section. And if you hit allow, then it puts a notification virus on your computer. Very easy to fix. And if you just simply hit block, then it's not an issue.
Weird. Yeah, and then it normally does not take this long to load. This is very unusual. The website usually loads really quickly. So I just open it up and it's loading. It's not doing anything. It's doing nothing. So
I can show how to fix it if anybody accidentally click allow.
Yes, let's have you do that. I think I should have it so you can share screen. Yep,
I can make my camera share screen.
Okay, you've got the power. Let me pin you so that you are nice and big for everyone. There you go.
All right, so this is with Edge. I'm not for sure if it's with other browsers, but if you have it set to where you can have notifications, where am I? My cursor? There it is. You go to site permissions, and then you just find it. It's the www.one.pushnews.org, and you just simply want to set it up to block notifications, and then that will fix the issue. I have not had any issues since then. I just I just went through and just blocked everything on it.
Okay. Yeah, I
And-
wonder if something went wrong with the website because I mean, this is a well-known publisher. He has this great website, and yeah, I can't even get it to load. So there's definitely something going wrong. I wonder if he got hacked. You know?
That's what I'm thinking. I ended up hitting allow, and then it just let me go, just took me to the website. But I'm thinking that it's making everybody click allow before it lets you use it.
Maybe, and I'm not even getting that. So I may have something because I've got our work computer. They may have blocked something, and that's why it's not even loading for me. So good to know. I will also have our IT people kind of investigate that and you know, do we need to remove the links to the publisher or what we need to do about that? But thank you for bringing that up. That's very helpful information.
It was just making a pop-up notification come on my screen like every 2-3 minutes. It's pretty annoying.
Anything else? Anybody else have any questions, comments, or anything like that? Okay, well, I will leave you guys. Oh, my chair is in the way. You are all positively amazing. You know, with Valentine's Day coming up, you got to have some affirmations here. I don't know how many of you guys are going to be watching the Super Bowl tomorrow, but it's going to be a busy weekend for lots of people, I imagine. So, all right. So you guys are welcome to pop off. I'm going to just, you know, stop the recording, and then I will email out the recording and the PowerPoint to you guys. So that way you have it for your notes.